So let's talk about the big O of bubble sort, a non-trivial algorithm. So this is a version of bubble sort from the 3A that I taught previously. You should be familiar with bubble sort even if it's not the exact same version as this one. Okay, so how does it, what is the big O of bubble sort? Well, we start obviously with the bubble sort itself, and we look at the implementation of bubble sort, and we see that there is a loop. And this loop, the number of times that it's going to repeat is the size of the input list minus 1. So that immediately you should see that that is kind of an O of n, right? In this for just the bubble sort itself. Now, even though we do have a minus 1 here, like we said many times already, we are not concerned with the minus 1 because minus 1 plus 1, whatever, some constant, they're going to become insignificant once the n is very big. So we can ignore the constant here. Now, the next thing we should pay attention to is that inside this loop, in each pass, we're actually going to call this function float largest to the top and give it a list. Okay. Now we also give it a size, and just kind of keep in mind that the size actually is the size starts out as the entire list, and then it gets decremented by 1 every time. So that sort of tells us, okay, we really need to look inside what flow largest to the top, how it works. All right, so let's look at that. Now, inside flow largest to the top, there is another loop, okay? And this loop, the number of times that we're going to repeat depends on the size, which is passed in from the bubble sort, and we start at just the size of the list, okay? So this the flow largest to the top, then because there's a loop that repeats n number of times, so that's kind of you should see that as kind of a O of n again. Okay, now you might say, okay, but size shrinks by 1 every time, right? Do we not have to worry about that? Well, not really, because again, if you think about it, this size here, even though it does become smaller and smaller over time, if the number of elements in list is bigger, then the size is bigger, which means this loop inside float largest to the top is going to repeat more times, right? Even though over time it's going to repeat fewer and fewer times, but still the size of list does affect the number of times that this loop loops. Okay, so that's why this is O of n and this is O of n. So when you put these two together, this is what we the loop inside a bubble sort is probably what we consider an outer loop. So, and the outer loop is O of n, and then the loop in the flow largest to the top, it's kind of an inner loop inside this outer loop, right? And that is O of n. So this means the number of repetition, the total repetition is really n multiplied by n, which is n squared. So that kind of means the O of n, the big O of bubble sort is on the order of n squared. Okay. Now, if you want to do the actual math, we can try that as well. So let's think about this. The first time flow largest to the top is called, it's it repeats n minus 1 times, right? Because if you look at this, yeah, n minus 1 times, and size starts at n. So the first time, largest to the for largest to the top, the loop inside it repeats n minus 1 time. Second time we call the same function, the size shrinks by 1. So this loop here, it repeats n minus 2 times. Third time, it repeats n minus 3, so on and so forth, until the loop only, at the very last time, the loop would only repeat 1 time. Okay? And so the total number of repetitions, if you want to add them together, is going to be n minus 1 plus the second time n minus 2, n minus 3, so on and so forth until the very last time, which is plus 1. Now, this is a number series, and if you remember your math, there is a formula for the sum of the series. If you need a little bit of review, this is a nice description of this formula here. So basically, the sum of this series, we can write it as n minus 1 times n divided by 2. And when you kind of group the n squared terms together and then the n terms together, we have something like, 1/2 n squared plus 1/2 n. And now, for the big O analysis, is that we are only concerned about the dominant terms. Now, between these two, n squared and n squared is going to be a lot bigger than n for large n, right? Let's say if n is 10, then 10 squared is 100. Well, this is still just 10, so 100 compared to 10, 100 is really kind of a dominating. Again, if you think about something even more drastic, like if this becomes 1,000, then if n becomes 1,000, then n squared is 1,000,000, and 1,000,000 compared to 1,000, well, 1,000 is really we really don't see it. So we can eliminate these insignificant terms, and we're left with 1/2 n squared. And then again, for big O, we're not concerned about the scaling factor in front of whatever function of n. Then we can now, the big O of n, the big O of this bubble sort is then now is just n squared, which is good because that's what we derived previously. So n squared is, it's kind of a slow algorithm. Bubble sort is probably the slowest sorting algorithm, and we'll study something faster later in the quarter. So all those are on paper that we see that bubble sort runs in the order of n squared. Now, so we should verify it, and this is the code to kind of measure bubble sort's performance versus the size. So for here, the size is going to go from 1,000, 2,000, all the way up to 9,000. And I'm going to generate some array of, kind of a random, array, list of random numbers, and I'm going to surround the call to bubble sort with 2 calls to performance counter. I'm going to print out the result. So I have the code here. I already ran it myself. I don't want to do it here. It's going to take a while. Anyway, here is the result from one run. And so that is, again, on the first column is the size, and the second column is the time that it takes. So, and if you plot it out, it kind of curves up. So this is a very telltale sign of something that is definitely not linear. It's something that is a polynomial. Now it's really hard to tell from the way that it curves here what what exactly is the polynomial, what is the power, right? Is it n squared, is it n cube, is it n 1.5 or some power? So, but usually, at least as far as this class is concerned, we are not terribly worried about the exact power here. And so as long as it looks like some sort of polynomial, we are fine. And you should definitely try to run this yourself and see it for yourself that our measurement kind of matches our theory.